Hey, what's up? Saturday night and another algorithm in your face. I am feeling like climbing a tree because it's the weekend, so that's what I'll be doing. And I want to climb a certain kind of tree, only a balanced tree. But the problem is that most trees are not balanced, so we're gonna have to make a make a balanced tree out of one of these unbalanced trees, and that is the problem I'm going to talk about tonight. Leetcode problem 1382, balance a binary search tree. If you like this video, well, if you like my work, like my videos, subscribe, like, and comment, and be sure to share. This helps me make more videos. Share it with your social networks and wherever else you think people could stand to benefit from learning how to balance a binary search tree and other algorithms that I do. I have many algorithms, and I'm going to plan on doing many more algorithm videos. So yeah, keep an eye out for those. And without further ado, let's get to this. Okay, so what is the gist of this problem? And this is a classical problem. It's labeled Leetcode medium. 590 likes, 29 dislikes. That means people like this problem. It's something that I believe shows up probably as a basic phone screen interview question for those people who are practicing algos for their interviews. And it's a very common problem in computer science where you have some sort of tree structure, and this is a tree, even though it doesn't look like a tree. It's a tree with every child node, a binary tree with every child node, that every child node has, every right node is populated with another node all the way up to the end. And it is a BST as well. It's not just any binary tree, it's a binary search tree, so it follows the binary search tree property, which says property that the left child is always greater than the root, and the right child is always greater than the root, and the left child is always less than the root, right, or less than equal. So the cool thing about a binary tree, search tree, is that you can search through the tree in log n time, right? So that's one of the advantages of having a data structure that is shaped in this manner and ordered in this manner, right? So that you can search through it quickly. But we have an unbalanced binary tree, and the reason why an unbalanced binary tree is not as useful as a balanced binary tree is because it takes longer, right? So logarithmically speaking, searching through an unbalanced binary tree, um, especially if it's unbalanced this drastically, will take linear time, right? It'll take the number of times of n in the node, and number of nodes there are. If there's n nodes, it'll take O of n time. In a balanced tree, and these are not too drastically different examples, so it actually won't demonstrate here, but if you look at like Google or whatnot, and you look at comparisons between unbalanced and balanced search trees, you'll see that a balanced search tree actually allows you to search through it closer to log n time. Okay, so that's why it's of practical importance to restore structure within a balanced tree structure, right? And so basically, it's a flatter tree. And in this case, a balanced tree has at most one difference. Every node, the depth of the two subtrees of every node never differ by more than one. So in this case, the depth of the subtrees, right, differ in increasingly in this unbalanced binary tree by 1, 2, 3. Okay. And this is, if you say the depth of this subtree on the left is 0, then the depth of this subtree on the right is 1, but that would be okay. If we had just this would be a balanced tree, but since we have another degradation through this right path, we have a descent through this right path, we have the depth being 2, depth difference being 2 here, and since the height is 0 here, we have a depth difference of 2, and here we have a depth difference of 3. In this case, we have a depth difference of at most 1 for each of the subtrees, right? Because a depth difference of 0 for this subtree, this 3 to 2 and 1 to 2, and a depth difference of 1 between this subtree 2 to 1 and 2, 3, 4. Okay, so the rightmost subtree and left subtree. And so if you look at a balanced tree, maybe you can look at a balanced binary tree. And you can look online that these are more balanced, right? Because if you calculate these, the depth is 1, at most 1, the depth difference between any two subtrees. So basically, these are more balanced. And this one to the left is is the best one, right? Kind of a full tree, and then this one to the right is more balanced because again, it really has a slight imbalance, right? And then this degenerate tree is the one that we so named as such because it's degenerated basically into a list that needs to be searched in linear time. Okay, so without further ado, that's a little bit of the prep work on the CS stuff. Let's get to the actual coding. Okay, so firstly, what do we want to do here, right? We need to reorder this tree, right? So how do we reorder any arbitrary tree? Well, firstly, in order to reorder the tree, we need to disassociate all the nodes from each other, right? So the first thing we do is create a disassociation function. I'm going to call it strip, okay? And I'll show you, I'm going to explain what the parameters are in a second, but strip will take in the root node, so we'll call that root, and then it will take in a list of integers, roots, which I will use as a variable to recursively store each of the individual roots of the tree as this tree is traversed. Okay, so basically, now in order to, here's the key thing. In order to, one of the major things about a binary search tree is that it can be traversed in order. So we want to maintain the ordering of these roots. That's very important in order to do a traversal, right? So how would we make sure that we can keep this array in order as we traverse through it? So first, we'll use our base case, root equals null, right? So if it's null, then we're at the end of a recursion. So for all you guys, recall your computer science knowledge, in order to traverse a tree and maintain the ordering of the nodes, you would want to do an in-order traversal, right? Remember, you have pre-order, post-order, and in-order, and they all serve different purposes. But in-order traversal, root.left, roots, an in-order traversal has your DFS to your left and to your right, sandwiching the active part of the function, which would be in the middle. Roots, okay? And what do we want to do? In the end of the day, we want to the roots, we want to add root.val, okay? Because what I'm doing here is I'm adding these roots in order, and this is guaranteed by the time this recursion is done to occur in order, okay? So so if I do strip, and let's just just for the sake of argument, right now I want to show you what strip returns. Okay, so I'm going to just print out strip here and run it. Obviously this will fail. 22 public void. This is a void function. Run code. So if given type strip. That's right. Sorry. I don't want to just pass in strip. I want to pass in my roots array, right, which will contain all the roots. So this will be an array list, and so we want to do strip root roots, okay, and then we want to print out roots. So let's take a look. And you notice when I print out roots here, 1, 2, 3, 4. This is the first example. All the roots are printed in order. And it doesn't matter which tree I use as the example. All the roots will be printed in order. Okay, so that's the cool thing about this in-order traversal here. So the next thing we want to do is restructure the tree. So this is where the tricky work comes in. So how do we restructure the tree? Okay, so first what we want to do, once we've stripped the tree down to its bare bark, per se, okay, we want to have a function that balances the tree, okay? So I'm going to call this the balance function. And I want to return a balanced tree. That means I'll return just the root node, which will contain all the other subnodes reattached to the new balanced tree. Okay, so that's what we're going to do. We're going to start reattaching the tree. So now I'm going to show you what I'm doing here. Int end. So basically, how would you balance a tree, right? Okay. So given an arbitrary list, right? Typically, you're given an ordered list of integers or whatnot. And in order to balance a tree, what you want to do is you want to... What is the balanced tree? A balanced tree is basically a tree that's even on the left and even on the right, or mostly even on the left of the tree and mostly even on the right for every subtree. So how do you do that? Well, if you have an array that's 1, 2, 3, 4, 5, 6, 7, 8, 9. How do I make this an even? How do I make this into an even tree? Well, first thing you can do is think about how would you divide this array, right? Because remember, one way you could do it for sure is put 5 in the middle and have everything to the right be the nodes to the right of 5, and everything to the left be the nodes that are to the left of 5. And there you go. So therefore we've made a split. We've created a new central node at 5, and we've created a list of right nodes that have everything to the right of 5, and left nodes that have everything to the left of 5. So we can continue this on. We can have 5, and then what we can do, how did we choose 5? We just picked the middle, the median, right? So we could do the same thing here. We could pick the median, right? We could pick the median, and in this case, the median would be 2, right? And then we'd pick 3, and then we could, and essentially, in this case, this 5 would be the parent here, and in this case, we would have 6. Actually, it probably would have been a better example to write out the whole tree, but write out a more complex array. But essentially, this is what we do. We keep picking the median of these lists, right? And by doing so, let's call it 1 and 3, 4 and 2. By splitting this up, and so on and so forth, we'd be able to, in the same way we do a binary search through this tree and rebalance it. So what I'm going to do, I'm going to say, I'll call this balance, return balance of roots 0 and roots.size minus 1. So what does that mean? So remember, in the binary search algorithm, you have, when you're looking for an element, you keep dividing the array into subsequently smaller halves, right? And you have to find, in each half, you have your midpoint, right? That's the important thing, to get the midpoint of your array. So with that being said, all we have to do is we have to recursively find the midpoint of our array. So what is the midpoint? Start plus end divided by 2. And this is the same as the binary search algorithm. You can look at that and find out how to find the midpoint of that array. So once we find the midpoint there, and what do we want to do first? Like, how do we want to end the recursion? Remember, in binary search, our recursion ends when the start the start index is greater than the end index. So basically, when the two halves overlap, that means there's no more searching to be done. You've gotten to the lowest level, the leaf of the search, right? Return. So return null. Okay. At that point, there's nothing else to return. And if we continue, we have this. And now, what do we do here? So tree node root equals new tree node roots that get mid. Okay. So I'm saying that I'm constructing a new root, and that's what I will return, right? Return this root. And what's the last thing we have to do here? Well, we're returning this root, but now we have to recursively, the recursion actually occurs when we're trying to get the left and right children. And the left and right children are successively recursive calls to the balance function, using as the input the original root array. But remember, as with binary search, we keep constraining the size of the subarrays, right? So we go to the left and we go to the right. So and remember, we're doing mid -1 and mid +1 because we're ignoring the central node, which is mid, right? Mid is here, is accounted in this line, and mid +1 and mid -1 to the left and to the right are accounted here. So pay close attention to what I'm doing here. This is the crux of understanding how this problem works, right? If this is the first half of the array, right? This is the left here, this start to mid -1, okay? If mid is 2 in this case for this 4-element array, right? To the left of mid is going to be everything this call is going to make, and that would be 1. So you would start at whatever start value you were initially, and you go to the mid 1 less than the midpoint. So that midpoint being 2, so you just take this 1 here. And in this case, you have the midpoint again being 2, so you go to the right. So this call to the right would call roots.right equals balance roots, which would be 3 and 4. Right? This would be mid, which is the center, offset by 1 to the right, all the way up to the end. Okay, so just review your binary search to see confirm how this works, but this is basically what we would have to do. Okay, so let's see how good we are with this problem. Okay, and it looks like that was accepted. All right, let's try it again. Everything else. And there you go, accepted. Faster than 28.43. Wow, not that great, right? I'm sure we could have optimized some things here, and I think see, I mean, also, like, sometimes this number here isn't always calculating everything, as best as possible. So you're never really sure, but like, generally speaking, we could probably do things faster. I just wanted to show you how we can come to a solution and create a balanced tree. And that's it for this problem. If you like this video, again, just give me a shout out and I'll continue to make more. With that being said, have a good night.